Alright, so this course is Introduction to Algebra. Today we're going to have a look at topic 1, some basic concepts in algebra. We'll talk about some basic concepts and methods. Okay, first of all, because we are dealing numbers in this course a lot, so let's have a look at the types of numbers. First, let me introduce you the main number systems. Probably some of you have already known some of the concepts here, so if in that case you can treat this as a brief review. Okay, all right, so at the very beginning, our humans conceived the set of natural numbers or positive integers as a consequence of the need to count things. For example, apples, thus came these numbers 1, 2, 3, right? And there also needs to be a symbol to express that there was no apples, thus came 0. So that leads us to the set of non-negative integers 0, 1, 2, 3, 5, or just positive integers 1, 2, 3, 4, or 5. So in that case, we have the first set of numbers, which is usually called the natural number set. Here, natural number set, which includes the numbers 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So be careful here. The natural number set has different definitions. Some people believe 0 is included. Others believe that 0 cannot be included. So there are two different types of definitions depending on the context. Okay, you should use the context to help you decide its exact meaning. Usually, when you see this letter N, that denotes the natural number set starting from either 0 or 1. So in that case, you need to use context to help you to decide which is true. Otherwise, when you see symbol N0 or N0, usually this denotes the natural number set starting from 0, which means this is a set of numbers of 0, 1, 2, 3, and so on. And when you see this number N1 or N star or N plus, usually this letter denotes that natural number set starting from 1. For example, N1 denotes a set of numbers 1, 2, 3, 4, 5, and etc. Can you follow me? Okay, by the way, if you have okay, can you follow me? Okay, so basically that's the meaning of the natural number set. Do you have any questions? And this seems enough for practical purposes in early times, but then humans would have also defined addition, subtraction, and multiplication or division. Because of man's innate curiosity, we had realized that the set of numbers thus far isn't complete under addition and is inverse, or subtraction. For instance, there is no number thus far which when added to 5 yielded 2, right? This is the same as saying when you have a number plus 5 equals 2. This doesn't have a solution. So in came negative integers. The set of all integers here, for example, -3, -2, -1, 0, 1, 2, 3, and so on, had a closure under addition or subtraction. So we call this set of numbers integer set, which is a larger set than the natural numbers. Can you see that? And usually we'll use letter Z or Z to denote the integer set. The integer set includes any number that can be written without a fractional component. Can you follow me? Okay, so that's an integer set. And however, this isn't yet closure under multiplication division, because when you have, for example, 5 over 2, this is apparently not integer, right? So we introduce another set of numbers, which is called the rational numbers. So the rational number set is usually denoted by the letter Q, which can be expressed as a fraction a over b, when a and b are both integers. And b is not 0 because we cannot use 0 as denominator, right? And as you can see here, the rational number set is larger than the integer set. And in parallel, if a real number that cannot be expressed as a over b, then this number is usually an irrational number. Or all real numbers which are not rational numbers are called irrational numbers. And both the rational numbers and irrational numbers are included in a larger set which is called real numbers. And usually we'll use the letter R to denote real number set. Okay? And of course, real number set subtracted by rational number set will give you irrational number set. Okay? And the largest number set is called complex number set. So we'll talk about complex numbers in the future lesson of this course. Okay? So currently we'll focus on discussion in the real number set. So as long as you know the real number set, you'll be fine. So real number set contains rational numbers or irrational numbers. Rational number set contains integers. And integer set contains natural numbers. You get it? Do you have any questions? Any questions, just let me know, okay? Let's see some examples. Okay, for example, we have already seen that the numbers 0, 1, 2, 3, 4, 5, all of these numbers are natural numbers, right? And -3, -2, -1, 0, 1, 2, 3, these numbers are all integer numbers. So you can just ignore the pure imaginary number set so far. We'll talk about this later, okay? And rational number set is a set of numbers that can be expressed as a fraction a over b. Therefore, all of these numbers, -3 over 5, for example, or -7 over 5, -1, 0, 1/2, or 4 over 3, or just 5, all of these numbers are considered to be rational numbers. And again, all of these numbers are contained in the larger number set, which is real number set. And you can imagine a number axis here. If we have drawn a number axis here, every point on the number axis corresponds to a real number. You get it? Can you follow me? Okay, so this is just a brief overview of the number system. And if you have any questions, just let me know, okay? Don't worry if you still feel a little confused about it. I'll give you my notes after the class, and if you have any questions, just leave me a message, okay? And there are some other trivial concepts about numbers. First of all, whole numbers. Probably in some textbook, you see the concept of whole numbers, but whole numbers is actually a colloquial term in mathematics. The meaning is ambiguous. It might refer to either natural number or integer. You need to determine its concept with the help of the context, okay? So whole number is not a very strict mathematical concept. And next, fractions. A fraction is used to represent the portion or part of the whole thing. It represents the equal parts of the whole. A fraction has two parts. The number on the top is called numerator, and the number on the bottom is called denominator. For example, the fraction 3 over 4. 3 is numerator and 4 is the denominator, right? Are we clear about that? And we have some trivial concept about fractions. First, unit fraction. Unit fraction means in a fraction, the numerator with 1 is called a unit fraction. For example, 1 over 2 or 1 over 4. Both of these two fractions are called unit fraction. Next, proper fraction. Proper fraction means if a numerator value is less than the denominator value, it's called a proper fraction. For example, 7 over 9 or 8 over 10. Are you clear? Okay, next, improper fraction. If a numerator value is greater than the denominator value, then it's called an improper fraction. For example, 6 over 5 or 11 over 10. As you can see here, the numerator 6 is larger than the denominator 5, right? Or 11 is larger than 10. So in that case, this fraction is called improper fractions. Next, mixed fraction. If a fraction consists of a whole number with a proper fraction, then it's called a mixed fraction. For example, 5 and 3/4, 10 and 1/2. All of these fractions are called mixed fractions. Next, like fractions means the fractions with the same denominator are called like fractions. For example, 4 over 2, 7 over 2, or 9 over 2. These fractions are called like fractions. You can actually combine them by adding or subtracting. We'll talk about this later, okay? And unlike fractions are fractions with different denominators. Equivalent fractions means if two fractions result in the same value after simplification, then they are equivalent to each other. For example, 2 over 3 and 4 over 6 are equivalent fractions, since when you simplify 4 over 6, you will get 2 over 3 as well, right? And next, irreducible fraction means it cannot be simplified. For example, 4 over 3 cannot be simplified further. So this is called irreducible fraction. And next, decimal fraction means the denominator is a power whose base is 10. For example, 8 over 100. This is called the decimal fractions. Again, this is just some trivial concept you should be able to tell. And I just want to make sure we are using the same math language when we talk about questions later, okay? Again, you don't have to write them down. I'll give you my notes after this class, okay? Do you have any questions? All right, next, some other concept related to numbers. Prime numbers, composite numbers, or neither. Do you know what a prime number is? Prime number, or prime in short, is a natural number greater than 1 that is not a product to smaller natural numbers. A natural number greater than 1 that is not prime then is called composite number. For example, 5 is a prime number because the only ways of writing it as a product is 1 by 5 or 5 by 1, right? Does not have other factors. However, 4 is composite because it's a product of 2 by 2 in which both numbers are smaller than 4, right? You follow me? Any questions? No? Okay. Good. Okay, last. Square numbers, or perfect squares. In mathematics, a square number, a perfect square, is an integer that is a square of an integer. In other words, it's a product of some integer itself. For example, 9 is a square number, or perfect square, since it equals 3 to the power of 2 and can be written as 3 by 3. And here are some examples in the scope of from 0 to 49. All of these numbers here on the right side are called perfect squares because they can be written as some integers squared. You see that? You have any questions? No? Any questions, just let me know, okay? And then let's do a quick quiz here to check your understanding, okay? So I'll give you 1 minute to try to complete this table. Tick in the corresponding blanks if a number on the left side belongs to that sets or categories, okay? And after that, we'll have a look at the solution together, okay? You can get a piece of paper and write down your solutions. And do you still remember the meaning of these symbols? N is a natural number set, Z is integer number set, Q is rational number set, R minus Q is irrational number set, R is real number set, right? C is complex number set. All right, have you finished? Okay, let's have a look at the solution together. Okay, negative 1.6. Apparently this is not a natural number, right? And not an integer as well, but it can be expressed as a fraction of two integers. So it's a rational number, right? And of course, it's also a real number. Any real number is a complex number, right? It's not prime, composite, perfect square, odd, or even, because these concepts are related to integers or natural numbers. -3 is not a natural number. Natural number must be 0, 1, 2, 3, or something else, right? So any negative number is not a natural number, but it's a integer, right? And any integer is a rational number. Any rational number is also a complex number. Is also a real number. Any real number is also a complex number, right? And it's a odd number as well. Next one, it's a fraction. A fraction is a rational number, also a real number, which is also a complex number. Okay, next number is 1. 1 is a natural number, which is also a integer and also a rational number, real number, complex number. Okay, number 1 is neither prime or composite, right? This is very important. The natural number 1 is neither prime or composite. You cannot put any ticks here, okay? And 1 equals 1 square, so it's a perfect square. And it's also a odd number. Next one, the square root of 3 is a irrational number because cannot be expressed as a fraction of two integers. So you should put a tick here. Any irrational number is also a real number and also a complex number. Next one, 2. 2 is a natural number, which is also an integer and a rational number, real number, complex number, right? And 2 is a prime number because you cannot find any factors other than 1 and 2 itself. And of course, 2 is an even number, right? Next one, pi. Pi cannot be expressed as a fraction of two integers, so that's a irrational number. Of course, that's also a real number, a complex number. 9. 9 is a natural number, also an integer, rational number, real number, complex number, right? And 9 equals 3 by 3, so it's a composite number. It's also a perfect square, and it's also odd, right? Okay, last one, 10. 10 is a natural number, a integer, a rational number, and a real number, a complex number. And 10 equals 2 by 5, which is a composite number, and it's not a perfect square, and of course it's an even number, right? Okay, have a look at the solution here. Do you have any questions? All right, if you don't have any questions, let's have a look at the next concept, order of operations. The order of operations is the rule that tells us the sequence in which we should solve an expression with multiple operations. A way to remember that order is PEMDAS, which means we should calculate the expression in the parentheses first, followed by exponents, multiplication, division, addition, and subtraction. So the order does not matter for these three. These three have the same priority, and these last two operations has the same priority, right? For example, if we have an expression like that, what is the final result here? Can you evaluate this expression? Okay, you can give me an answer in the chat box, okay? Leave your answer here in the chat box. Okay, when you finish, give me your answer in the chat box, okay? And then we'll have a look at the solution together. Okay, let's have a look at solution together. So this equals, remember we need to do the expression in the parentheses first. So just leave the other expressions as it is. So here we have 5 times 9, right? Plus 2 minus, at the same time we can calculate 6 divided by 2, which gives us 3, right? And this equals 4 minus, we have 4 by 9 is 45 plus 2 minus 3. And this gives us 4 minus 47 minus 3, which gives us negative 46, right? Okay, Vincent. What is the final result, Vincent? Is it negative 40 or negative 46?
Negative 46.
Yes. Okay, please correct your solution by yourself, okay? Alright, any questions? Okay, if no questions, let's have a look at the next concept. Properties of operations. We have some properties of addition and multiplication. So addition and multiplication are commutative, which means if you change the order of the operand, the result is the same. For example, a plus b equals b plus a. The order does not matter. Or a multiplied by b equals b multiplied by a, right? So remember, if there is no ambiguity, you can omit the multiplication symbol. So basically, AB is the same with A times B or A times B. Okay, you can use either notation here. And both the addition and multiplication are associative, which means if we have A plus B plus C, you can calculate the sum of the last two numbers first, or you could also calculate the sum of the first two numbers first. And same thing for multiplication. A times the product of BC equals the product of AB times C, right? Have you ever heard of this before? Yeah, I guess you already know this, right? Okay, good. Then for any three numbers, A, B, and C, the distributive property applies for multiplication and addition, which states that if we have A times the sum of B plus C, then we can distribute A into the parentheses. This equals A times B plus A times C, right? This is called the distributive property. Or sometimes you could also have A plus B times C, and the same thing applies. That equals AC plus BC, right? This is another form of distributive property. And next, factoring. Factoring is a process of reversing the distributive property. When factoring, we take a common factor out of each term in a sum and write the result as this factor times a simpler sum. For example, if we have an expression a times b plus a times c, then there is a common factor a, right? So we can put the common factor in front, and what's left in the parentheses are the sum of these two numbers, b plus c, right? It's just a reverse process of the distributive property. Do you have any questions? Okay, if you have any questions, please interrupt me, okay? I need to make sure you can follow me, all right? Okay, and there are some properties of operations for the exponents as well. Common properties of exponents are listed as follows. So for example, we have two numbers a and b belongs to the real number set, and two other numbers m and n also belongs to the real number set. Whenever the expression is meaningful or defined, well, by meaningful or defined, I mean, of course, you could not use a negative number under the square root symbol. So far, we only talk about the problems in real number set, right? So in real number set, you can't have any negative number under the square root symbol, or you could not use 0 as the denominator, okay? Other than that, we have these properties listed on the right. First of all, if we have a to the power of n times a to the power of m, if the base numbers are the same, we can combine this exponential expression to a to the power of m plus m. For example, 2 to the power of 3 times 2 to the power of 2 gives us 2 to the power of 5, right? Why is that? Because 2 to the power of 3 is simply 2 by 2 by 2, right? And 2 to the power of 2 equals 2 by 2, right? Of course, 2 to the power of 3 times 2 to the power of 2 gives us the product of 5 2's. So that equals 2 to the power of 5, right? You follow me? Of course, this can also expand it to the real number set. For example, if we have 2 to the power of 1 over 2 times 2 to the power of 3 over 2, this still gives us 2 to the power of 1 over 2 plus 3 over 2. This is also correct. Which is 2 to the power of 2, right? Okay, next, if we have a to the power of n over a to the power of m, this gives us a to the power of n minus m. For example, 3 to the power of 8 over 3 to the power of 2 gives us 3 to the power of 6. Can you follow me? Have you learned this before? Kevin? Have you learned this before? Okay, if you have any questions, just let me know, okay? And if we have a to the power of n, then to the power of m, then we can combine these two exponents to a to the power of n times m. For example, 5 to the power of 4, then squared. This gives us 5 to the power of 4 by 2, which is 5 to the power of 8. You follow me? And if we have a times b, then to the power of m, this gives us a to the power of m times b to the power of m. For example, 3 times 5 to the power of 7 can be detached to a product of two numbers, which is 3 to the power of 7 times 5 to the power of 7. And next, a over b, a fraction, raised to the power of n. This gives us the numerator to the power of n over the denominator to the power of n. For example, 2 over 3 to the power of 5 gives us 2 to the power of 5 over 3 to the power of 5. And next, a to the power of negative n is simply the reciprocal of a to the power of n. So that equals 1 over a to the power of n. For example, 2 to the power of negative 1 is actually 1 over 2 to the power of 1, which is 1 over 2, right? And next, a to the power of n, 1 over n, is actually the nth square root, nth root of a. of course, your value of a must make this nth root meaningful. Okay, for example, 2 to the power of 1/3 is actually the cubic root or the third root of 2. And next, a to the power of n over m is actually the mth root of a to the power of n. For example, 2 to the power of 3 over 4 is simply, well, first you raise the number 2 to power of 3, then find its fourth root. And of course, any number to the power of 0 will give us 1 except 0. So here a cannot be 0 because 0 cannot be the denominator, right? For example, 5 to the power of 0 will give us 1. You follow me? Okay, make sure you are familiar with these properties when evaluating expressions related to exponents, okay? Do you have any questions here? Sunny, any questions? Jacob? Vincent?
Well, I think I have a question.
Yes.
Like, I still don't understand the the power of minus n.
This one?
And and also the 2 below, the 2 equation below.
2 equation?
Like a the power of n 1 over n.
Oh, here.
And also a n over n.
These two, right?
Okay. And also a the power of 1 over n.
Oh, okay. Okay, I'll explain this a little bit. This one, and this one, right?
Yeah.
Okay, first one, a to the power of minus n is actually a to the power of 0 minus n, right? Which is a to the power of 0 over a to the power of n, right? Can you see that? Can you see why? Because we have the first property here, right? So a to the power of 0 gives us 1. So that equals 1 over a to the power of n, right? Does this solve your question? So we have explained this, right? Okay, next one. A to the power of 1 over n. Yeah, because the second one, a to the power of 1 over n to the raised to the power of n gives you a. Therefore, we know this number in the parentheses is actually the nth root of a. Okay, then combine the two expressions, we can have the next one. Okay, the next one states that a to the power of n over m. So this can be expressed as first a to the power of n, right? Then raised to the power of 1 over m, right? And we already explained this. Anything raised to the power of 1 over m is actually the mth root of that number. So that equals, first you raise the number a to the power of n, then find its mth root, right? Does it make any sense? So that explains this one, right? Okay, so make sure you are familiar with these properties. So let's do some exercises involving these properties, okay? Check your understanding here. Again, I'll give you 2 minutes, and after that, we'll have a look at the solution together, okay? Try to evaluate or simplify each of the following expressions using what we have learned so far. Okay, let's do this together. You can compare your results with mine, okay? 15 minus 3 is 12. 12 over 2, we can just leave it there, times 3, minus 2 to the power of 2 is 4. 4 by 3 is 12. So 12 over 6. So this gives us 3. 6 times 3 minus 2, which is 18 minus 2, which is 16, right? Second one, first we can calculate 8 minus 13. This is negative 5 times negative 3. This gives us positive 5, right? Can you follow me? Okay, next one, we have two different ways to calculate that. Of course, you can find the sum of these numbers first, then divide it by 11, right? Otherwise, you could also factorize each number to 9 by 11 plus 8 by 11 minus 11 by 7 plus 11 by 6. Then, as you can see here, we can cancel 11. First, put 11, the common factor in front, then we have 8 plus 9 minus 7 plus 6, right? Divided by 11, then we can cancel 11 here. Then we get 16, right? And next, 2 to the power of negative 3 is actually 1 over 2 to the power of 3. Then times 2 to the power of 2. This gives us 3 to the power of 2 over 2 to the power of 3. This is 9 over 8, right? You follow me? Okay, next one. So note that the exponents are the same, but the base numbers are not. So this gives us 5 times 6 times 2 together, raised to the power of 1 over 2, right? And this is 60 to the power of 1 over 2. Or you can also write it like square root of 60, right? And square root of 60 is actually 4 by 50. Square root of 4 by 15, so we can put, so that equals square root of 4 times square root of 15, right? And square root of 4 is actually 2, so eventually we have 2 times square root of 15, right? Can you follow me? Next one, 2 to the power of 5 over 2 is 2 to the power of 5. Then find a square root, right? Because it equals 2 to the power of 5 to the power of 1 over 2. This gives us 2 to the power of 5. Then find its square root. And then 2 to the power of 5 is 2 to the power of 4 times 2, right? Square root of 2 to the power of 4 gives us 2 to the power of 2 outside. Then times square root of 2. So this gives us 4 times square root 2, right? And last one, note that we have, well, these two numbers seems to be different, but actually we can convert that to 1 over 2 to the power of 2 times negative 3 to the power of negative 1 first, then to the power of 2, right? So this gives us 1 over 2 to the power of 2 times negative 3 to the power of negative 1 gives us negative 3, the reciprocal of negative 3, right? Then to the power of 2, so this gives us 1 over 2 times negative 1/3 together to the power of 2, and of course this gives us 1 over 36, right? Can you follow me? Do you have any questions? Okay. Yeah, because we are running out of time, I think we'll just omit these exercises. You can take a snapshot here and try to finish this after this class, okay? Any questions, just send me a message. Take a picture of that or write this down onto your notebook. Try to finish them after this class, okay? And there are some others here. Okay, I'll put them in the same page. Have you finished? Okay, if you haven't finished, you can find them on my notes. Okay, I'll give you my notes after this class, alright? And next, let's have a look at another concept, which is expressions and equations. Again, let's have a look at the concept of concept is two terms here. In math, an expression or mathematical expression is a finite combination of symbols that is well formed according to rules that depend on the context. Math symbols can designate numbers or constants, variables, operations, functions, brackets, punctuations, and grouping to help determine order of operations and other aspects of logical syntax. Here are some examples of expressions. 3 plus 8, this is the expression. 8x minus 5, this is also expression. 7x squared plus 4x minus 10 is also expression, or x minus 1 over x squared plus 12 is also expression. Usually when you don't know a number, we could use some letter to denote that number. And these letters here, for example, the x is here, usually denotes a variable, which means it can be assigned to different values. You understand? And on the other side, a equation is a statement equating two algebraic expressions that might be true or false depending on the values substituted for the variable or variables. Values of the variables that make the equation true are called solutions or roots of the equation. All of the solutions to an equation comprise the solution set of the equation. An equation that is true for all possible values of the variable is called an identity. Okay, we'll talk about equations and how to solve an equation later in this course. So currently don't worry about the solution of an equation, okay? So here I just want to use an example to illustrate terms here. For example, if we have 3x squared equals 9, when you have this symbol here, this is called an equation, which means the left side equals the right side. And the values that make this equation be true, for example, in this example here, x can be either positive or negative, square root 3, right? These values that can make this equation true, so these values here are called the roots or solutions to that equation. And the solution set is the set contains these two numbers. Usually we'll use this number, we'll use a pair of parentheses like this to denote a set. So when we want to express a set of several numbers, use this symbol here, okay? And when a set does not contain any elements, you could use this symbol or this symbol to denote the empty set, which means there is no element in that set, all right? And identity is a equation that is always true. For example, x minus 2 squared is always x squared minus 4x plus 4. And again, we'll talk about this later. If this expression is always true, then we can call it identity. Okay? Are you clear? Again, these are just some generally used terms in mathematics. Okay? Make sure we are on the same page. Alright, then there are some properties of equations. First, the symmetric property of equation tells that if A equals B, then of course we will have B equals A. The order of the two elements on both sides of the equality symbol does not matter, right? It's pretty straightforward, right? If you have A equals B, of course you will have B equals A, right? And next, if C is any number and A equals B, then all of the following equations are true. First of all, A plus C equals B plus C. Well, remember, this is a condition. If we have A equals B, C is a number, then if we add the same number to both of the original equation, the new equation is also true, right? You understand? And of course, if you subtract both sides with the number C, this equation is always true. And if you multiply both sides using the number C, this equation is also true. And if you divide both sides using number C, this equation is also true. Of course, in the last case, the denominator cannot be 0, right? And if we have a fraction A over B equals C over D, then we must have AD equals BC. Can you see this? Can you see why? Because if we have A over B equals C over D, we must have A over B times this number BD equals C over D times this number BD, right? Of course, originally, if we can see B and D are in the position of denominator, so B and D, of course, both of them are not 0. So this number here is not 0, right? Then we can cancel a B here, cancel a D here. This gives us A, D equals C, B, or BC, right? You follow me? And if A equals B and C equals D, then we have the following expression are true. A plus C equals B plus D, A minus C equals B minus D, and AC equals BD. And last, the transitive property of equality tells us that if A equals B and B equals C, then we will have A equals C. Alright, so please have a look at the property here and let me know if you have any questions, okay? You can try to prove them by yourself after this class. I'm not gonna talk about the proof here, okay? All right, if no questions, let's have a look at another concept, which is formulas. Many equations are often referred to as formula or formulae, and typically contain more than one variables and often other symbols that represent specific constants or parameters. Parameters are constants that may change in value but do not alter the properties of the expression. Formulae with which you are familiar include, for example, the area of a circle, d equals rt, or distance equals the square root of the coordinates of 2 points. Don't worry if you don't know that. We'll talk about this later in this course, okay? And the volume equals 4 over 3 pi r squared, volume of a sphere. Whereas most equations that we encounter will have numerical solutions, we can solve a formula for one variable in terms of other variables, often referred to as changing the subject of the formula. Again, these are just the concept of some terms, and don't worry about the equations or formulas here. We'll talk about this later, okay? All right, then let's do some exercises. Can you evaluate each of the following expressions? So note that all of the languages here are called mathematical expressions, right? We can evaluate their values when x equals 6. You know how to do this? We simply plug x equals 6 into each of the equations, right? Each of the expressions, right? And also, sometimes people use equations and expressions interchangeably. So first of all, x equals 3. Well, x equals 6, we have 6 plus 3, right? And that gives us 9. 2x is actually 2 times x equals 6, so we'll have 12, right? And evaluate the third one. X squared is actually 6 squared, and plus 3 will give us 36 plus 3, so this is 39. And x plus 12 over x is 6 plus 12 over 6, and that's 18 over 6, which is 3, right? And 3 times x squared is 3 times 6 squared, which is 3 times 36, which is 108. Last one is square root of 5 times 6 minus 5, which is square root of 25. Of course, this will give us 5, right? Okay, do you have any questions? All right, if not, let's have a look at another exercise. Can you simplify the product y squared times y to the power 4? And simplify the product 2x times 3x cubed. Write v cubed to the power 5 as v raised to the power of single power. And last, write 2x to the power of 3 as a constant times some power of x. Okay, have you finished? If you need more time, just let me know, okay? Alright? Okay, first of all, remember we can, if the base numbers are the same, we can combine this to y to the power of 6, right? And next one, 2x times 3x squared, we can combine them to 2 by 3 is 6, then times x to the power of 4, right? And next one, v to the power of 3, then to the power of 5. Remember, we have a to the power of n, then to the power of m equals a to the power of the product of n times m, right? So this gives us v to the power of 15. And last one, we have, remember, we have a times b to the power of n gives us a to the power of n times second number to the power of n, right? So this equals 2 to the power of 3 times x to the power of 3, and this gives us 8x cubed. Any questions? Do you have any questions? No? Alright, then let's consider some other exercise. Can you simplify each of the following expressions? And okay, I'll put them in the same page, okay? There are two other questions here. Okay, let's have a look at the solution together. We can compare yours with mine, okay? The first one is, if the base numbers are the same, x to the power of 7 over x to the power of 3 will give us x to the power of 7 minus 3, right? So that's actually x to the power of 4, right? Can you follow me? And next one, we can cancel 4 with 20, so we have a 5 here. Then that gives us 1 over 5 times x to the power of 9 minus 2 is 7, right? So that is x to the power of 7 over 5. And next one, 5 can be cancelled with 20, and we have 4 here. 4 cancel with 8, we'll have 2 here. So we'll have a constant of 6. 3 by 2 is 6, right? Then let's have a look at the t's. So we have t to the power of -3 times t to the power of 4, which means we add a 4 here, over t to the power of 8 means we minus 8 here, then plus 12, right? So this gives us 6 times t to the power of 5. You follow me? Any questions? No? Okay. Next one, can you simplify this expression here? The cubic root of 27 times x to the power of 9. And then suppose r is positive. Can you simplify this equation, this expression? 200r to the power of 10. This first one is the cubic root of, well, you need to express the number under the cubic root to any number to the power of 3, right? So 27 is 3 to the power of 3 times x to the power of 2, x to the power of 3, then to the power of 3, right? So actually this gives you cubic root of 3x cubed to the power of 3, right? Well, which means 3 to the power x to the power of 3 to the power of 3. Remember that the cubic root is actually raised to the power of 1/3, right? And then we'll have 3x cubed. Well, these two numbers, the product of these two numbers is 1, so that equals 3x cubed, right? Can you follow me? Ben? You understand? Okay, Sunny? How about you? Jacob? Okay, Kevin? Do you understand? Vincent? Do you understand?
Yes.
Okay, so how about the second one? Square root 200r to the power of 10. Again, we can express the number under square root to something squared, right? Note that we have 100, 2 times 100 is 200 times r to the power of 5, then to the power of 2, right? So that equals 10 times r to the power of 5, then square times 2, then finally square root, right? And that gives us 10r to the power of 5, then square root 2, right? Any questions? Okay. All right, then let's have a look at another concept. GCD or GCF and LCM. We'll use these terms a lot. In mathematics, the greatest common divisor is called GCD. That is the GCD of 2 or more integers which are not all 0 is the largest positive integer that divides each of the integers. For two integers x, y, the greatest common divisor or GCD of x and y is usually denoted as GCD of x, y. So you can consider this as a function of two variables x and y. For example, the GCD of 8 and 12 is 4, right? Because we know 8 is 2 by 2 by 2, 12 is 2 by 2 by 3. Both of them have a factor 4, and 4 is the largest possible common divisor. So GCD of 8 and 12 equals 4. Can you follow me? And for another example, 12 and 18. The GCD of 12 and 18 equals greatest common divisor is 6, right? Can you follow me? And the least common multiple on the other hand, lowest common multiple or smallest common multiple of two integers a and b, usually denoted by LCMAB, is the smallest possible integer that is divisible by both a and b. For example, LCM 8 and 12 equals 24. You clear with the concept now? Also note that relationship between LCM and GCD of two numbers a, b can be expressed as this. LCM, the least common multiple of a and b, equals the absolute value of the product of these two numbers divided by the greatest common divisor of these two numbers. For example, let's consider these two numbers. A equals 8, b equals 12. Then we know the absolute value of the product of these two numbers is 96, right? and the GCD of 8 and 12 equals 4, and LCM can be given by this formula, which is 96 over 4 equals 24, right? Can you follow me? So as long as you know the GCD, greatest common divisor, then it's very easy to find the LCM, right? Can you follow me? So the problem is, how do you find the GCD of two numbers? Okay, let's talk about how to find the GCD of two numbers. For example, sometimes it's very simple, right? But sometimes for example, if I want to find GCD of 24 and 16, how do you find that? And for another example, okay, let's talk about 24 and 16 first. How do you find the greatest common divisor? Usually, when the numbers are not very large, we can factorize each number, right? So 24 equals 4 by 6, and 16 equals 4 by 4, right? So note that there are some same factors for 6 and 4. So 4 by 2 by 3, and 16 equals 4 by 2 by 2. So the greatest common divisor should be 8, right? This is just the easiest case. And sometimes the numbers are so large that we cannot see the greatest common divisor at the first glance. I'll give you an example. How about GCD of 1071 and 462? How about that? What is the greatest common divisor of 1071, 462? If you have the answer, give me your answer in the chat box, okay? Give me your answer in the chat box when you finish. Any thoughts there? Of course, you can also try to factor each number, right? And try to find the common divisors and then find the greatest common divisor, right? But this is very time consuming when the numbers are very large. So there is a shortcut which is called a Euclidean method we can use to find the greatest common divisor. I'll just mention it here. You can have a look at that after the class. Or if you feel confused, don't worry about that. We'll talk about this a lot in our later lessons, okay? So here I'm gonna give you some introduction to this method. So first of all, we can use 1071 as a dividend and 462 as divisor. Then find the result here. So probably we can put a 2 here, right? Then if you put a 2, you will get 9, 2, 4, right? And find the remainder. 11 minus 4 is 7. 6 minus 2 is 4, and you will have 147 as the first remainder, right? Then use the 462, the divisor, as the new dividend divided by the remainder here. Then try to find the result and remainder again. So here we can put a 3 here, and we will get a 4 4, 1, right? Then we'll have the remainder as 1, 21, right? Then that's the second remainder. Then use the divisor as a dividend again, divided by the remainder you get until you find the remainder is 0. So in this case, we can just put a 7. Then that gives us 14, 7 here. Then remainder is 0, right? So we can stop here. Then find the last two remainders if you have that. When you have two remainders, when you have more than 3 remainders or 3 remainders, use the last two remainders to find the GCD of these two numbers. So the GCD of the last two remainders, 147, 21, is the GCD of these two numbers. The GCD of 147 and 21 is 21, right? You see that? Because 147 can be divided by 21, right? Therefore, the GCD of the two original numbers should also equals 27. So this algorithm is called Euclidean algorithm, which is used to calculate the GCD of any two integers. Again, here is just a brief overview. If you want to know more about that, we'll talk about this in our later class, okay? So when you have only 2 remainders here, or less than 2 remainders, then we'll use the second to the last remainder as the GCD of these two numbers, okay? But so far, as long as you know the first method, you should be fine, all right? Okay, then if you know the GCD and LCM, then we can talk about the next concept, which is to simplify or reduce fractions. The fraction is in its simplest form if the greatest common factor of its numerator and denominator is 1. That is, if they share no common factors other than 1. For example, 3/11 is in the simplest form, since 3 and 11 have no common factors other than 1, right? However, 6/21 is not in the simplest form, since 6 and 21 share a common factor of 3. Are you clear with the concept? So sometimes we can reduce or simplify a fraction, right? Very straightforward concept. And a fraction is in its simplest form if the greatest common factor of its numerator, we have already talked about this, right? Simplest form of a fraction. And next, let's have a look at how to reduce the fraction. To reduce the fraction, divide both the numerator and denominator by the GCF. This is also known as writing a fraction in lowest terms. This is sometimes shown as canceling the common factors. For example, let's see the previous example, 6/21. We know 6 can be written as 3/2, and 21 can be written as 3/7, right? We have a common factor 3, so we can just cancel the 3 here. So this leaves us the simplest form of that fraction, which is 2/7, right? Note that the result is an equivalent fraction in the simplest form. Are you clear with the concept here? Okay. Any questions? All right, let's have a look at the next concept, which is writing the fractions in a common denominator. Sometimes we can write the sum or difference of 2 or more fractions in one single fraction with a common denominator. Usually, we shall use the least common multiple of the two denominators as a common denominator. For example, 5/12 plus 2/15. How do we write this fraction in a common denominator? We find the least common multiple of the two denominators, which is, can you find that? Least common multiple, 12 and 15. Apparently that's 60, right? LCM of 12 and 15 is 60. Then 5/12 is actually, well, in order to have denominator to be 60, we need to multiply 5 to 12, right? And in order to keep the fraction unchanged, you need to multiply the same number to the numerator, right? Plus 15 times 4 gives us 60. And in order to have a same fraction here, we need to multiply the same number to the numerator. So that gives us 25 over 60 plus 8 over 60, right? Which leaves us 33 over 60. And of course, we can cancel a 3 here, right? So that leaves us 11 over 20. That's the final result, simplest form. Can you follow me? Okay, next, how do we write the second in a common denominator? So note that the least common factor of 16 and 8x is 16x, right? So 16 times x, x times x, minus 3 times 2, and 8x times 2. This gives us x squared over 16x minus 6 over 16x, which gives us x squared minus 6 over 16x, right? You follow me? Okay, so last, let's do some exercise, and then we can complete the class. Okay, okay, consider this example here. There are some expressions. Evaluate or simplify each of the following expressions. Okay, I'll give you 1 minute to think about that, and after that, we'll have a look at the solution together, okay? All right, then let's have a look at the solution here. We know 63 can be cancelled with 7. That leaves us 9, right? Then 9 can be cancelled with 63 here, which leaves us 7 here. So this is 4 over 7, right? Or you can just directly cancel 63 here, 63 here. Again, we'll have 4 over 7. Next one, 4 by 12 is 48. This can be cancelled with 48 here, so we'll have 1 over 97, right? And next one, this can be written as 63 times 7 minus 5 times 9 over 63. So this gives us 14 by 40, minus 47, 45 over 63, and that's negative 31 over 63, right? And next one, we can cancel a 3 here and an r here, right? So that is r squared minus 7 over r, right? And last one, we can cancel a x, so that gives us 3x plus 9 over 4x squared plus 12x, and 3x plus x, 4x, x plus 3, and then cancel x plus 3. That gives us 3 over 4x, right? Of course, x cannot be 0. Here, r cannot be 0, right? Okay, and if you have no questions, let's consider one last exercise. Okay, can you write each of the following expressions as a single fraction? Okay, let's do this together. Okay, first of all, the greatest common factor of, the least common factor of x cubed and 5 is 5x cubed. Then this leaves us 2 by 5 here plus so this gives us 3x to the power 4 plus 10 over 5x cubed, right? Next one, the least common multiple of the two denominators is 15y squared. Okay, this leaves us 23y minus 15 over 15y squared, right? Okay, next one, the least common multiple of the two denominators is s by s plus 2. And this gives us 3s plus 6 minus 7s squared over s times s plus 2, right? So far, you can just leave it here. In our next few lessons, we'll talk about probably you need to check whether you can factor that to a product of two expressions. And last one, this is, well, the least common multiple is z by z minus 1, right? So that gives us 2z times z minus 1 plus z times z minus 1. And we have 3 times z minus 1 here, minus z minus 2 times z here, and z times z minus 1, right? And try to find the final result by yourself, okay? Because this kind of problem is pretty straightforward, and try to find the final result by yourself. All right, so today we just talked about some basic concepts related to algebra, and in our next lesson, we'll talk about how to solve linear equations and very simple one variable equation. Okay. And I'll also give you some exercise questions after this class. And when you finish, please submit your solutions to our VChat group, okay? And I'll see you next time, then have a great weekend, okay?